Hey, what's up, physics students? We're going to learn about vector addition today. Vector addition. Now let's remind ourselves what a vector is all about. We've learned a lot about vectors actually already. We've learned that acceleration, velocity, displacement, and something else maybe, but at least those three, right? Displacement, velocity, acceleration, they're all vectors. That means, remember what a vector has. It has a magnitude and a direction. Right? So when you're a vector, when you're a quantity that's a vector, whether you're talking about any of those three I just mentioned, or force, hello, there's another vector, right? You have an amount, which is a magnitude, and you have a directionality, east, west, south, left, right, up, down, 180 degrees, 90 degrees. Those are all considered to be directions. So if you got both those things, then you are a vector. And if you are a vector, then these rules that we're going to learn about today apply when you're trying to add vectors. So let's get into Roman numeral 1, which is, let's go ahead and say vector addition methods. Vector addition methods. Okay, now there's one primarily that we use above all else. And then there's another one that I'll show you real quickly that we don't use as much. Sometimes we use it to visualize. So the first one that we're going to use most of the time, 99% of the time, is head to tail vector addition. Head to tail vector addition. And simply put, that's what it is. You take all your vectors and you make sure the head of one of the vectors is lined up on the tail of the other vector, and you do that as many times as you need to put all the vectors together, and then you figure out the answer, which we'll get to. So I guess we could say by placing, this is the definition of head to tail vector addition, by placing the tail of one vector on the head of another, and then rinse and repeat as many times as you have to do that, you can find the resultant vector. Now, what is this resultant thing? That's the answer. You can find the answer vector, basically, right? The resultant, the answer vector, by drawing a vector from the tail of the first. Oh my gosh, so many words. The tail of the first vector to the head of the last vector. Okay. That is a lot to say and to write, but let's demonstrate what is meant by all this verbiage, right? So let's put some vectors down. You might be saying, well, why are we getting into this specialized unit called vector addition, right? We've been learning about vectors, but everything we've done so far, if you recall, is in one dimension, right? We're in one straight line. Well, now we're blowing the doors right off of that, and we're saying you don't have to stay in a straight line. You don't have to stay in the x-axis only. You don't have to stay in the y-axis only. Now we can break into, let's be in both axes at the same time. Let's have diagonal velocities. Let's have diagonal forces, diagonal displacements, because so far we haven't had that. It's always been perfectly in the x-axis, perfectly in the y-axis, and nothing in between, right? Nothing in between. But now with this new method, we can talk about things that are in the in-between, so to speak. So this will be called vector A, and I'm being really general. Please hear me on this. I'm not saying this is a velocity vector or an acceleration vector or a force vector. I'm just simply saying it's some general, generic vector called vector A. That little hat is just a symbol that means it's a vector. This will be vector B, some general vector. Could be any kind of quantity that has a magnitude and a direction, right? And we'll have vector C. And we want to use this new method to put vector A, vector B, and vector C together. Head to tail. So by placing the tail of one vector on the head of another, you can find the resultant vector. So I'm going to start there. Placing the tail, let's take the tail of B and put it on the head of A. Right, that's what it says to do. Place the tail of one vector on the head of another. So I'm going to put the tail of B on the head of A, and I'm going to take the tail of C and put that on the head of B. So it would look something like this. When you decide to do, let's go ahead and add these together. So I'll say A plus B plus C. What does that look like? Well, it looks like this. Now, it's very important when you add vectors to maintain the direction and the magnitude, right? Because that's what a vector is, a magnitude. What is the magnitude here? It would be the length of the vector, right? You got to maintain that length. You can't change that length. That's set. And also, you see how it's kind of going up maybe at, I don't know, what is that, like 35 or 40 degrees, something like that, right? It's pitched up at an angle. You have to keep that same pitch when you put all these vectors together. So you have to maintain, that's its direction, right? And its length, which is its magnitude. Now let's take the tail of B. Let's get back to the point here. The tail of B. And let's put it right here on the head of A, like so. So now we have vector A with its head on the tail of vector B, with the tail of C on something like that, right? On the head of B. And you'll see what happens when I add all these vectors together. You get this picture. Like, okay, well, all right, well, what is this resultant vector all about? That is the final answer. Okay, so let's say this was a force. We're pulling with 40 newtons this way and 15 newtons this way, and we're pulling with 30 newtons this way. Well, what is the resulting force that comes from all of those forces at one time? Right? It would look like this. You go from the tail of the first vector, as it says right here, a vector, drawing a vector. So you can find the resultant vector by drawing a vector from the, oh, there should be a from there. That's why I'm confusing myself. From the tail of the first to the head of the last. There's our resultant vector. And I'm going to call it vector R for resultant. Right? That would be the answer in this case. And so, okay, that's great. Notice we don't have any numbers yet. I haven't got to the mathematical part of this. I just want you to be able to visualize what's happening here. Here's another example we could attach to these generic vectors. Let's say I walked 40 meters this direction, kind of at this angle, right? If I was calling that north and I was calling that east, right? I'd kind of walking in a northeastern type of path for 40 meters. And then I walk for 20 meters due east, and then I walk for 30 meters due south. Well, by the end of the trip, what's my final resultant? What's the result of all of those different displacements? It would be that, right? It'd be a resultant vector that's that much. And you can see if I'm assigning this 40 meters, that looks like it's maybe 50-ish, right? Maybe 50 meters due east. And so that's the whole point of this vector addition, is to be able to take angled vectors now, put them all together, and then come up with the result. Now the next question is this: could I have added these vectors visually in different ways? Yes, we could have. So here I did A plus B plus C, and I'll call that example 1. Right? Let's look at example 2. What if I looked at, I don't know, C plus A plus B? Could I have done it that way and still arrived at this result, that answer? Let's find out. So I'm going to take C. I'll put it right here. I'll start with C. There's C. Vector A is next. So vector A, its tail will go on the head of C, right? Head to tail vector addition. So we're looking something like that. You've got to really maintain that, the same directionality and the same length. Same direction and the same magnitude. That's the same thing as length. And let's see here. Yeah, let's go ahead and let's put in vector B now. Let's put the tail of B on the head of A, and we have something like that, right? something like that. Maybe it's a little longer, maybe like that. B. Do we get the same answer? Well, I have to start at the tail of the first vector that I used to add, right? And go from there to the head of the last. That's what it says here to do. Go from the tail of the first vector that you started your vector addition with to the head of the last vector. That's your resultant. And I'm going to kind of elevate above this so it doesn't confuse you. Kind of go a little bit higher than the vectors themselves. Look at that dotted line I just drew, which I'm calling the resultant. Doesn't that pretty much look the same length as that resultant there? There's one resultant, there's another, and you can see it's the same exact result. So this is the beauty of vector addition. It doesn't matter the order in which you add them. You can add them in any order that you want, as long as you maintain the magnitude and direction of the vector, you're gonna get the same result. And if you really wanted to try another one of these, you could do like B plus C plus A, right? B, in fact, shoot, what the heck, right? B plus C plus A, right? There's B plus C plus A. And don't you agree that's pretty much the same result right there? You don't need to draw this one. That's just more example. If you want to, you can call it example 3. Just make sure if you draw that in your notes, you put B plus C plus A, right? Because that's B, that's C, and that's A. So going back up to the very top of the notes, the vector addition methods, these are really visual. None of these are mathematical, right? We're not really putting numbers with these yet, so these are visual techniques. Visual vector addition methods. If you want to squeeze the word there instead, you want to do that, that's fine, but we're looking at visual vector addition techniques right now. So let's come up with some conclusions. We could say, as long as the magnitude and direction of the vectors are maintained, because you have to maintain them, can't change the lengths or the directionality of them, the vectors can be added in any order. Any order, cool, all right. And really there's a slick way to refer to that, but if I had said that, it wouldn't have made any sense to you. This idea that you can add them in any order is to say that vectors have no location, which sounds weird, right? But what it's saying is you can pick them up and put them together like little building blocks however you want to. You don't have to have them located in one spot, and you can still get the same result, right? So we could say this means vectors have no location. Done. All right. So that's head to tail vector addition method. There is a second visual vector addition method, and it is called parallelogram method. So we'll write that's our numbering system. Let's write number 2 on here. And we'll call this the parallelogram method. Now there is a distinct disadvantage of the parallelogram method. And I'll say it right now so we don't have to figure it out later. Disadvantage is only 2 vectors can be added at a time. Only 2 vectors can be added at a time. How do we do it? What's the method? Here's the method. I'm going to write that next. Place the tails of 2 vectors together. See how that's different than the last method? Place the tails of 2 vectors together. And draw a parallelogram. Going from the tails to the opposite corner of the parallelogram I'm just going to write these parallelogram lines, parallelogram. I hope that makes sense. I just wrote parallelogram fast there. To the opposite corner of the parallelogram, the resultant can be found. The resultant vector, I'll say, can be found. All right, done. So let's go ahead and try that out. Let's use the same exact vector so you can see that even this method can get it done. Again, there's the disadvantages right up here. So we'll draw vector A. And here I'm only going to do one example. I'm not going to do a bunch of examples. I think vector A looks something like that. Vector B was something like that. And vector C was something like this. And once again, I know I already said it, these are just general vectors. I mean, these could be velocities, right? We could have velocity that's pointing this direction, like that could be the wind shear on a plane. Actually, maybe that could be the wind shear. Maybe this is the velocity of the plane, and it's experiencing some wind like this. And maybe this is a flock of seagulls that hit the front of the plane. I don't know, maybe that's kind of talking about force though, right? We're talking about something hitting something. So maybe this is just another wind. I don't know, you got two different winds. You got this wind and you got this wind hitting a plane trying to do this. See, these vectors could be just general they could be anything. They could be forces, velocities, displacements. And we're trying to see what's the result of all of these vectors acting at the same time. All right, let's go ahead and get into the method. So I'm going to draw a parallelogram using A and B first. So I'll write A plus B real fast. And using my new rules, not the head to tail rules that we just learned, my new rules say, I'll take my vector A, something like that. And I'm going to take the tail of B and place it on the tail of A. So it looks like that. And now I need to draw a parallelogram. Oh, there you go, now you can see it. Parallelogram would look something like that. We're drawing parallel lines. These two lines are parallel, those two lines are parallel. Now how do I get my resultant vector from this? You go from the two tails, going from the tails, right here, the tails you put together to the opposite corner. So now I'm going to draw this opposite corner answer right here, and I'll fill that in actually. That is not the answer yet. Okay, that's not the answer yet. All right, this I guess I'll just call A plus B, so we're not trying to come up with like vector D or some other letter. Let's just keep it to A, B, and C. So that's A plus B. That's what it looks like using this new method. And again, only two at a time, that's kind of a pain. So now I'm going to take my new A plus B vector and redraw it over here. So let's see if I can get this guy pretty much the same. There's my A plus B, right? And now let's throw down C. C, oh, I almost messed up. I almost went head to tail vector addition. Don't do it, I just tried there. Do draw this though. Draw your A plus your B. And now draw your C. Now the tail of C will go, guess what? Right there on the tail of A plus B. So it looks like that. And now we have to draw another parallelogram. There's my other parallelogram. And what do you know? What do you know? Going from the two tails that we're touching to the opposite corner of the parallelogram, that's my resultant. That would be, by the way, this would be A plus B plus C, right? Using this parallelogram method. And if you look back, as long as I maintained the lengths and the directions of these vectors, doesn't that result right there? That R right there, that length, doesn't that look pretty much like that length to you? Right? There's another example of R. There's R, right? And what do you know? Looks pretty much the same length. So this method works. We're never going to use it. You might see a question on multiple choice about parallelogram method. Sometimes I do refer to it to help us visualize an answer, but we don't make much use of it. Enough said. Now, you know this is physics. You know the language of physics is mathematics. So we can't keep the math out forever, although you might be enjoying not having the math in it. We're going to use the head to tail concepts to finally get into the math. All right. Do we need visual vector addition? That's the question. Do I really need this method called head to tail method that I taught you about right away at the beginning? The truth is you don't really need it to do vector addition problems, but it helps you to visualize the physical situation. I'll say it again. The head to tail method helps you to visualize the physical situation, and it helps you to double check that you're doing your math right and that you're getting a reasonable answer based on the visual that you drew.